Hey Team Pekin, and welcome to today's lecture, where today we're going to discuss general principles of spectroscopy with a specific focus on vibrational spectroscopy. And so let me pick up with some of our takeaways from last lecture, where we talked about this harmonic oscillator model. The reason we brought this model up was because it's a good model for studying bond vibrations. If we have two atoms, then their bond can be modeled as a spring. And in this case, the potential energy that holds these two atoms together can be modeled as a quadratic potential. You'll notice that our model has two different parameters associated with it. One parameter tells us K, which is the spring constant, or in more chemical terms, this bond strength constant. So if K is really large, it's going to be hard to move these two atoms away from their equilibrium bond distance. Versus if K is small, it's pretty easy for this molecule to stretch and compress. And then secondly, our next parameter, Re, tells us what the equilibrium bond distance is for this particular pair of atoms. And you'll notice that there is, because of the quadratic potential, it takes just as much energy to stretch the bond a certain amount as it does to compress it. Last lecture, we also solved for the wave functions and associated energy levels of this harmonic oscillator model. And what we found was that the wave functions were a product of these Hermite polynomials, which gives each wave function a certain amount of oscillatory behavior, times a Gaussian function, which tells us that the wave function should decay as a Gaussian as we move to larger and larger displacements. The energy levels themselves are pretty simple. We have that the energy level is given by nu, our vibrational quantum number, plus 1/2, times h bar, Planck's constant, divided by 2 pi, times the square root of k, again that's our spring constant or our bond force constant, divided by mu. And in this case, mu represents a reduced mass, which is the product of the two masses for atom A and B, divided by their sum. The other kind of fun fact that we learned about this harmonic oscillator model was that due to the energy levels themselves, all of the energy gaps between successive levels have the exact same value. And that value for the energy gap was equal to h bar divided by k by the square root of k, h bar times the square root of k divided by mu. And so that's great to have this model, but now we have to contend with taking this model and helping it to understand a real infrared spectrum for a real molecule. And so as an example, I'm going to be using CO2 as our molecule of choice. For any infrared spectrum that you might be interested in, NIST is a really great source in order to look up these experimental spectrum. But nevertheless, we're going to use this spectrum to help guide us in today's discussion. When I look at this spectrum, especially if the only thing I have in my mind is the harmonic oscillator model, I have a number of questions. And these questions are not all going to be addressed in today's lecture, but I do hope that between today's lecture and the next lecture, that we'll get to understand them more deeply. Some of the questions that we want to ask when we're talking about vibrational spectroscopy is first, why the infrared region? Why does that help us understand the vibrational motions of molecules? The second thing is, you'll notice that up until now, our harmonic oscillator model has just been for two atoms. Carbon dioxide has 3 atoms, and we'd want to be able to study infrared spectra for more polyatomic systems. So how is it that our harmonic oscillator model, if at all, can be applied to studying these larger systems? A third question that we might have is, what does the harmonic oscillator tell us about the position and the shapes of these peaks, if anything? Why do I get different peaks in my spectrum? Why do these peaks have different intensities? Why do the peaks have different widths? And why is this x-axis presented in a unit system we haven't seen up until this point in this course? What is a wave number, and how does it relate to either wavelength, something we're more familiar with, or the energy gap associated with these transitions? Over the next 2 lectures, we're going to try and tackle all of these questions. And for today's lecture, I'm going to tackle the questions that you can see on the slide that are shown in orange, blue, and purple. We're going to hold off on these green questions until next lecture. Okay, so let's get started. Because we're going to be talking about a lot of general principles today, I'm going to use vibrational spectroscopy for many of my examples, but I am going to introduce some of these principles as they relate to all different types of motions that you might expect a molecule to experience. And generally speaking, there's 4 different types of energy transitions you could see a molecule undergo. We highlighted these in the last lecture, but it's worth going into them in a little bit more detail. So the first type of motion is translational motion. This would be my carbon monoxide molecule moving back and forth in either the X, Y, or Z direction without changing any of the internal coordinates. So in translation, you don't change bond lengths and you don't change bond angles. You just move the molecule along one or multiple of your Cartesian coordinates. Energy transitions in this type of motion corresponds to the molecule either gaining or losing kinetic energy. And at the very beginning of the course, the model that we discussed that had no potential energy and that was purely kinetic was a particle in a box. And so that particle in a box model is a great way to understand the energies and wave functions associated with translational motion. And in particular, we actually did a homework problem on the motion of N2 in a box, and we saw that for most molecules, while translation is technically quantum mechanical, it can often be modeled classically. A second type of motion, which we haven't touched on in this course, but will be the subject of a couple of lectures from now, is rotational motion. This would be my carbon dioxide molecule spinning about its center of mass. Again, we're not yet changing bond angles or bond lengths, but we are allowing the molecule to rotate. And just like translation, molecules can rotate in many different directions. So I could spin my carbon dioxide molecule about an axis so that the oxygen atoms move quite a lot, or I could spin it along the Z direction, and you'll see that there's not too much motion in the rotational sense. I'm not going to have too many of my atoms displaced far away from their original positions. Energy transitions, again, for a rotational motion, cause the molecule to be able to spin faster or slower. And you're going to see in an upcoming lecture that the model we'll use to understand the quantum mechanical nature of this motion is called the rigid rotor approximation. Vibrational motion and electronic motion are 2 types of motion that we have seen a little bit more in class. Vibrational motion now finally is where we get to change the positions of the internal coordinates. So a vibration could be changes to either the bond lengths or the bond angles within a molecule. And we saw in the last lecture that the harmonic oscillator was a great way to mimic these vibrational motions. I've sort of hinted in this direction, but next lecture we're really going to unpack some of the limitations of the harmonic oscillator. And so I want to highlight here that there are alternate models that you can use to study these vibrational motions, and the Morse potential is one that we'll discuss in this lecture series. And then last but not least, we have our electronic motion. Here, none of the positions of the nuclei are going to move, but the electrons, especially the valence electrons, which are most prone to undergoing changes, we're going to have electrons in the valence that are either excited up into a higher energy orbital, or if the molecule starts in an excited state, those electrons are able to move back to the ground state. We've seen in this course that there's many ways to model this electronic motion depending on the system that we're talking about. Are you dealing with an atom? Those H-atom wave functions are probably the most appropriate way to describe this electronic transition. Are you talking about a dye molecule? Well, to rough approximation, we could probably use particle in a box once again to model this behavior. Or if we have computational resources, we can then use MO theory or computational chemistry to help give us insight into what these electronic transitions would look like. One thing that really helped me when I was starting to understand spectroscopy was understanding that these different types of motions have very different energy gaps. And so, as far as possible, this figure shows these energy gaps drawn to scale, although you'll notice our electronic energy levels on this scale are so large as to extend way off the paper. Translational energy gaps are something on the order of 10 to the negative 40th joules. This is so small that I can't even draw an arrow to represent this energy gap. I just have to draw a little dot, and even then that's too big. Rotational energy levels and vibrational energy levels tend to have energies that are, for rotation, on the order of 10 to the negative 23rd joules per transition, so per atom or per molecule. And vibration is about 3 orders of magnitude larger, something on the order of 10 to the negative 20th joules. And then last but not least, electronic energy transitions are something on the order of 10 to the negative 18 joules, which is an order of magnitude that you've seen when we were discussing the hydrogen atom. And so as we think about these different energy scales, once we correlate this to the associated wavelengths of light that would be produced, either emitted or absorbed during these transitions, we can start to understand why different parts of the electromagnetic spectrum help us understand different types of molecular or electronic motion. In particular, if we put these typical orders of magnitude onto our electromagnetic spectrum, you'll notice where we start to get different types of spectroscopies. Electronic transitions occur somewhere between the visible to UV light spectrum. Sometimes you may extend just a teensy bit into the X-ray part of the spectrum, depending on the nature of your electronic transition. And so when folks talk about UV-vis spectroscopy, typically what they're studying is electronic transitions. You'll also notice that vibrational transitions, photon energies on the order of 10 to the negative 20 joules, occurs in the infrared part of the spectrum. And so for this reason, when we talk about IR spectroscopy, you can use it as synonymous with vibrational spectroscopy because of the typical energies associated with these transitions for molecules. And then last but not least, we have rotational energies somewhere on the order of 10 to the negative 23rd joules, and the appropriate region of the electromagnetic spectrum to study these transitions is the microwave region. And so again, you'll hear folks in the literature use microwave spectroscopy as a synonym for rotational spectroscopy. Last but not least, you'll notice that I tried, but kind of failed because of the x-axis scale, to plot where we would expect to see typical translational energy gaps. And the radio waves that you would need are simply too large for humans to produce. So while translational motion in principle could be studied, practically speaking, it doesn't get measured, and you don't see translational spectroscopy as an active area of study. So now that we've understood a little bit about why it is that our infrared spectroscopy is the appropriate way to tackle the vibrational motions of a molecule like carbon dioxide, it's time to understand that x-axis. As in different fields of chemistry, and I can do nothing other than apologize that we, as a chemistry community, didn't settle on a more universal set of units, spectroscopists love dealing in a unit system called wave numbers. And so all of these different aspects of a photon, its wavelength, its frequency, its energy, or as we'll soon see, its wave number, they are all talking about the same identity of a particular photon, but they use Planck's constant, some combination of Planck's constant and the speed of light to translate between different unit systems. Some of these we've seen before. E photon, that's our photon energy. It's going to be identical to the energy gap associated with a particular translation, with a particular energy transition. We can convert that to wavelength if we take Planck's constant times the speed of light divided by the energy of the photon. Or, as you're going to learn as new today, if we want to translate the energy of our photon into units of wave numbers, then a wave number is 1 divided by the wavelength. In other words, we can take the energy of our photon, divide it by Planck's constant and the speed of light, and that'll give us our wave number. Infrared spectrum are often reported not only in units of wave numbers, but in units of inverse centimeters, which means that we have to be very careful when we do these unit conversions so that we don't make mistakes. And so along those lines, let's do a quick example. One of the peaks in our IR spectrum for carbon dioxide is located around 2340 inverse centimeters. What is the energy of the transition that produced this peak? And does that fall into the sort of 10 to the negative 20th joules that we would expect for a photon energy, given that we expect this to be a vibrational transition? So what we want to do in this case is we have our wave number, and wave numbers are typically reported as a nu for frequency with a little tilde over the top, so you know it's in wave numbers. If our wave number is 2340 inverse centimeter, the first thing that we want to do before converting to our photon energy is put everything in SI units so that our energy will ultimately end up in joules. And so since there is, let me write this for my own peace of mind as 2340 divided by centimeters. Since there are 100 centimeters per 1 meter, that tells us that we have 234,000 inverse meters for our wave number. Converting this to our energy of a photon, what we need to do in order to isolate the photon by itself is apparently to take the wave number times Planck's constant and times the speed of light. Meters per second, and 234,000 inverse meters. So you can see how my units are going to cancel. And after I punch these numbers into my calculator, the ultimate result is that I would get this energy of this photon to be 4.37 times 10 to the negative 20 joules. And so that lines up pretty well with this rough order of magnitude that we gave for what we would expect the energy of a vibrational transition to look like. All right, now that we understand the x-axis associated with our IR spectrum and why we're in the infrared, it's time to understand a little bit about why we see the peaks the way that we do. Two things that I want to focus on in this moment is first, noticing how different peaks in the spectrum have different intensities. That is a measure of how much absorbance we expect for a particular peak. In other words, an understanding of why these peaks have different lengths on the y-axis. And I also want to understand a little bit about the various different line widths that show up. Shown in blue are, the width of this peak on the x-axis. We want to understand, in general terms, what factors control these quantities so that we can see if there's any useful information to be gleaned by either the intensities or the line widths that we expect to see in a spectrum. There's a couple of factors that determine the line width of a peak, and they are as follows. These are three of the big ones, but there might be additional factors that are relevant to different types of spectroscopies. One factor is our friend the Heisenberg uncertainty principle. We talked earlier in this lecture series about the uncertainty principle that tells us that we can't simultaneously know position and momentum, but there's also an uncertainty principle associated between time and energy. Because the time that an energy transition takes and the energy associated with that transition can't be both known simultaneously, typically there's a little bit of uncertainty associated with the energy of a transition, leading to a broadening of the peak in the spectrum. And that's especially pronounced for fast transitions, where the more certainly we know what that time of the transition is, the less certainly we can know what the energy of the transition is. A second effect that influences the line width of a peak and leads to peak broadening is called the Doppler effect. The most famous application of the Doppler effect is actually, if you've heard ambulances go by, you'll notice that the tone that they have when they're coming towards your house or your apartment sounds different than when it's going away from your apartment. So the frequency of a sound or of light is going to change depending on whether the molecules that you're trying to take a spectrum of are moving towards your detector or away from your detector. And that leads to a little bit of broadening in our associated peaks. And then last but not least, molecular collisions can also lead to peak broadening in the spectrum. This is especially pronounced at high temperatures and high pressures, or if you're taking a spectrum of something that's present in aqueous solution, because other particles can provide or take away energy from the molecule that you're studying, and that's going to modify the transition energy slightly. And all of the factors that influence the energy of the transition lead to a little bit of peak broadening, since the x-axis represents effectively the energy associated with a particular transition. So one takeaway that we can have from this is we can't control the Heisenberg uncertainty principle. We can't control the Doppler effect, but we can control the degree to which molecular collisions occur in our spectrum and in the experiment that we're doing. So if you really want to get the narrowest peaks possible that can be more easily resolved so you can more precisely locate where an energy transition is occurring, low temperature gas phase spectroscopy is your best bet. Moving on to the intensity of the IR signal, again, that's going to be in the Y direction. How much absorbance does a particular peak lead to? The intensity of the IR signal is basically telling us how many transitions occur in our sample. And that's fundamentally related to the probability that a certain transition is expected to occur. We've talked a lot about probabilities in this course, and so we can understand a little bit about where these intensities are coming from. And there's three main factors. One factor is the intensity of the radiation of the appropriate wavelength to induce a transition. If you have a really weak light source, you're not going to be sending too many photons into your sample that have the chance to be absorbed by the molecule and produce that energy transition. So the more intensity, the more absorbance you're going to get in your spectrum. A second factor is the number of molecules that are in the appropriate state to either absorb the energy you're interested in or emit that energy. If all of our molecules are present in the ground state because we're at low temperature, and you want to study the vibrational transition between nu equals 5 and nu equals 6, that's going to be really hard to do because there's not going to be very many molecules that start off in the right state. And it's very improbable for a molecule to go from the nu equals 5 to the nu equals 6 state if it's not even probable for it to be there in the first place. So we have to have a number of molecules in the appropriate state, and you can control that as an experimentalist by increasing the concentration of your sample, for example. And then last but not least, a really important factor for determining these transition probabilities is the square of the transition dipole moment. This is a new expression for us, and mathematically, the square of the transition dipole moment, mu angle brackets of t, is equal to the integral over all space of the complex conjugate of the wave function corresponding to the final state of the molecule times something called the dipole moment operator times the wave function of the molecule in its initial state. And so hopefully you can see a little bit of similarity between the expression that's shown for the transition dipole moment and Ehrenfest's theorem, which helped us calculate averages. And so that's where you see this angle bracket notation showing up one more time. However, this transition dipole moment is really new for us and is worth talking about in more detail. And so the expression for the transition dipole moment is not something we're going to derive in this course. I'm only going to tell you that where it comes from is the time-dependent Schrödinger equation. It's a measure of how effectively a molecule in an initial stationary state, psi I, sub I, can couple with an electric field or couple with that electromagnetic radiation, light, in order to induce a transition to a different final state, psi sub F. And so that way of expressing the probability that the light can interact with a molecule in such a way to give it energy to go up to a higher state or help it release energy to go back down to a lower state is called the transition dipole moment. And its reason for depending on the dipole moment itself is related to some of the classical physics that you did in your electromagnetism course. But what's important for us to know as budding spectroscopists is that if this transition dipole moment is 0, light absorption or light emission cannot be used to induce a transition between states. And so on principle, it's possible for that molecule to find another way to change energy levels. It can't be induced spectroscopically. And in the literature, we call this a forbidden transition. In practice, forbidden transitions are either not observed at all spectroscopically, or they have very weak intensities associated with them. On the other hand, if our transition dipole moment is non-zero, the transition is expected to occur, and it's referred to as an allowed transition. Allowed transitions have much stronger spectroscopic signals. And one thing you may want to ask is, well, how strong of a spectroscopic symbol? And why is it that different peaks in the IR have different intensities? Well, for allowed transitions, the magnitude of the transition dipole moment squared determines the intensity of the spectroscopic signal. And that in turn is going to depend on sort of the overlap between the initial and the final wave functions and the dipole moment itself. Is there a large dipole moment that can be induced as this molecule interacts with light, or a small one? Numerically evaluating the transition dipole moment is an exercise for computational chemistry. We're going to get to explore that next lecture and in class. However, what we can say in a lecture sense, and not having to evaluate these intervals explicitly, is it's usually possible to analyze the conditions under which transition would be expected to be allowed, our transition dipole moment being non-zero, or forbidden, having the transition dipole moment equal to zero. And so what factors or conditions lead to this interval being zero or non-zero are collectively referred to as selection rules. And as you might imagine, the selection rules depend both on the type of spectroscopy that we're performing and on the model, in some cases, that's used to try and get a sense of what the wave functions for the initial and final states would look like. So as we go through the remainder of the course, I'll be bringing up these selection rules for different types of spectroscopy as we discuss each type of spectroscopy in turn. So for today, we're talking about vibrational waves functions and vibrational energies. So we're going to end off today's lecture talking about vibrational selection rules. All right. And so our selection rules for IR spectroscopy are derived from these wave functions that we discussed at the very beginning of today. It's those Hermite polynomials times the decaying Gaussian. For IR spectroscopy, you can mathematically show that there's two conditions that have to be met in order for a transition to be allowed in the IR. The first condition is that the vibrational motion must induce a change in the molecule's dipole moment. How you can mathematically represent that is to say that if we change some of the internal coordinates of a molecule, that had better change the dipole moment. The dipole moment, again, is something that you've discussed both in your physics classes, where you gave it a mathematical formula. Mu is equal to the sum of all the charges of the individual particles times their position in space. And we want that somehow to change as we change our internal coordinates. So the best way to try and explore the selection rule is by doing a couple of examples. Our first example is going to be O2. It turns out that vibrational transitions in O2 are forbidden transitions. In other words, O2 is not active in the IR, and you would not observe any peaks associated with an oxygen molecule were you to perform a spectrum of that molecule in that vibrational region. The way that we can understand this is that because there's no electronegativity difference between the two oxygen molecules, there's no dipole moment. And it doesn't matter how much I stretch or compress this oxygen molecule, there will never be a dipole moment in O2. And so you don't see this molecule, and you can't observe it using IR spectroscopy. On the other hand, carbon monoxide is a molecule that's IR active. If you remember from general chemistry, oxygen is more electronegative than carbon, and so oxygen has a partial negative charge associated with it, carbon, a partial positive charge associated with it. That helps us draw a permanent dipole moment associated with this carbon monoxide molecule, and if we stretch or compress this molecule, that dipole moment is going to change, Again, because it's related to the charges, the partial charges on these atoms, times their positions in space. And so because bond stretches or compressions change this dipole moment, CO is IR active, and we would expect to see a transition in the IR that corresponds to the energy associated with CO moving between vibrational energy levels. And in fact, we sort of did an example of this in the last lecture. If we can see where that peak shows up in the IR for carbon monoxide, we can relate that back to the bond force constant K associated with carbon monoxide and use the results of our experiment to understand a little bit more about just how strong that triple bond is in carbon monoxide. And then last but not least, select vibrational motions of carbon dioxide end up being IR active. We're going to mostly hold off on discussing polyatomic molecules until next lecture, but I want you to see how for complex molecules, certain motions or changes in the internal coordinates can lead to the formation of a dipole moment, whereas other motions are not expected to lead to a dipole moment. And so let me show you two different motions. The first motion that I'm representing on the left is a bending motion. And so the black arrows are intended to help you visualize what this would look like. Essentially, if our carbon atom stays the same, we have the oxygen atoms moving up above the plane and down below the plane. So that might look something like this when the molecule is in the middle of its transition. And while carbon dioxide in its equilibrium set of positions doesn't have any dipole moment, remember we have two individual dipole moments pointing from each carbon to each oxygen, but those cancel each other out exactly. It doesn't lead to a net dipole moment. All of a sudden, when carbon dioxide is allowed to bend, the bent carbon dioxide does have a small dipole moment. And because this vibrational motion causes a dipole moment to appear and disappear, that means that this type of motion is IR active. And in fact, if we wanted to scroll back up to our spectrum, I'm going to highlight for us that it's this peak that shows up somewhere around 600 wave numbers that corresponds to that bending motion. On the other hand, another type of motion, what's called the symmetric stretch, ends up not being IR active. A symmetric stretch is, again, where we're going to hold the middle carbon still, and we're going to allow the oxygen atoms to move out simultaneously or move in towards one another simultaneously. And unfortunately, while each of the CO bonds has a dipole moment associated with it, those dipole moments in the symmetric stretch are going to cancel each other out, regardless of whether we're stretching or compressing. So the symmetric stretch motion doesn't have an associated dipole moment or change in the dipole moment as the vibrational motion occurs, and that means that the symmetric stretch is not IR active. If this motion were to occur, you can use computational chemistry to show that this peak would show up somewhere around 1400 wave numbers. And now I can show you what a forbidden transition looks like in the IR. You'll notice that there's this basically non-zero, but itty bitty peak that shows up in the IR. It's kind of unclear from the spectrum. Is this part of the noise or is this a real signal? That's where our symmetric stretch would be, and because it's a forbidden transition, we don't see a peak associated with it in the IR. And so this rule about dipole moments helps us understand one of the two necessary conditions for making a vibrational motion IR active, but it's not the only condition. It turns out there is also a selection rule associated in particular with the harmonic oscillator model that says that the transition dipole moment integral is only expected to be non-zero if we are traveling between successive energy levels. And so our vibrational motion says that it is allowed to transition between the nu equals 0 state to the nu equals 1 state, but it's not allowed for us to transition between the nu equals 0 to the nu equals 4 state, because that would require us to move up many different energy levels. it's not only those energy levels that are associated with, it's not only absorbance that's allowed by IR spectroscopy. It turns out that our emission motions are also allowed. But again, what we want to see is the molecule transitioning between an excited state and a less excited or a ground state, such that we're only moving between successive energy levels. Now, of these levels, it turns out that at room temperature, most molecules are in the vibrational ground state. And so it's the transition or the absorption between the ground state and the first excited state that is the most probable and that shows up in the IR spectrum with the most intensity. Hence, this is called the fundamental transition for a molecule. And so if you hear about the fundamental vibrational transition, have in your head that that's always a transition either from the ground state to the first excited state, or if you start off with all the molecules excited, the emission from the first excited state back to the ground state. Okay, and with that is all that I have to discuss for today's lecture. This was a lot of information, so let me summarize some of our most important takeaways. One takeaway is we learned that different types of motion, either molecular motion, where we're moving the positions of the nuclei, or electronic motion, where we're moving and changing the energy levels of an electron within a molecule, correspond to different parts of the electromagnetic spectrum. If we want to observe electronic motion, we better pay attention to the UV-vis part of the spectrum. Those energy changes are something on the order of 10 to the negative 18 joules. If we're interested in vibrational motion, it's the IR spectrum that we're interested in, corresponding to photon energies of 10 to the negative 20th joules. And lastly, if we're interested in rotational motion, we better pay attention to the microwave part of the spectrum, with energy transitions on the order of 10 to the negative 23rd joules. Because there are so many different unit systems associated with spectroscopy, it's probably also helpful to point out where we expect to see different transitions and their corresponding wave numbers. So you'll notice that vibrational transitions occur between 100, maybe close up to a couple of thousand wave numbers. Electronic transitions have larger wave numbers, and rotational transitions are more on the order of 10 inverse centimeters. A second major takeaway for us is that the shapes of the peak in a spectrum, in particular the line widths, how much this peak spreads out on the x-axis, and the intensities, how big this peak is on the y-axis, or how much absorption is associated with the peak, are governed by many different factors, some of which we can control as experimentalists, and some of which are a little bit out of our control. The intensities in particular are important to understand so that we as spectroscopists can predict whether a certain type of motion is even able to be observed using a certain type of spectroscopy. These ways of knowing whether or not a transition is allowed or forbidden are referred to as selection rules, and it's helpful for us to be able to know what peaks to expect and which peaks or motions we might be able to computationally predict but not experimentally observe. And then last but not least, our third takeaway for today is that because we are currently focused on vibrational spectroscopy, I introduced to us the selection rules associated with IR spectroscopy. Our two selection rules, both of which have to be met in order for a transition to be observed, is first of all, that the vibrational motion must lead to a change in the dipole moment of a molecule as the motion occurs. And secondly, that the change in the vibrational quantum number has to either grow by 1 or shrink by 1 in order for the transition to be allowed. And again, because we're going to challenge this assumption in the next lecture, I want to be clear that this second selection rule is assuming a harmonic oscillator molecule. If a molecule roughly obeys that harmonic oscillator model, but has some differences associated with it, or the model isn't perfect, this second selection rule turns into more of a strong suggestion rather than an absolute rule, and you might expect to see weak transitions in this so-called forbidden region, not because our transition dipole moment was anything wrong, but because the wave functions that we plugged into the transition dipole moment to get this rule weren't quite perfect because of the limitations of our model. And so with that, that's all that I've got for us today. Next lecture, we're going to pick up with a couple of the questions that we weren't able to address in today's lecture. Namely, next lecture, we're going to try and understand how the harmonic oscillator model can be used to help us understand the positions and shapes of these different peaks, and we're going to see how this harmonic oscillator can be applied to polyatomic molecules. And last but not least, we're going to spend a little bit of time challenging the assumptions of the harmonic oscillator model and see if we can't do just a little bit better if we're willing to put in a little bit more work. So with that, take care, folks, and I look forward to seeing you in class.